Hi, my name is Jeremy. I am a Postgres engineer at GEICO.
Hi, my name is Leo. I am a CloudNativePG maintainer.
We're going to be talking about an exciting feature in cloud native Postgres called failover quorum.
And you definitely need to know it if you use synchronous replication.
Okay, hello and welcome. Today we're going to be talking about quorum-based consistency for cluster changes with the cloud native Postgres operator, or more broadly, we'll be talking about running Postgres on Kubernetes. My name is Jeremy. I am a Postgres engineer at GEICO.
And my name is Leonardo. I'm a software engineer at EDP.
And before we get started, I do want to put one quick plug in. Just want to mention that I think this is a really exciting time to get involved with the cloud native Postgres open source project. I just off the top of my head, I put like 10 areas on this slide right here, which are places where you could make meaningful and impactful contributions today that a lot of people would benefit from. In this talk, we're just going to be talking about one of these areas, which is the cluster management and failovers. But there's a lot of stuff going on. It's a fun time to be over here. I'm going to go first. And what I'm going to do is give kind of a high level overview of things. And then I'm going to talk about the design. And then I'm going to hand it over to Leo. And Leo's going to dive in a little bit, talk about how it works under the covers. So let's get started. First of all, before we get started, there's kind of two things that I need to talk about to set the stage, okay, and to give a little bit of background. The first thing is just to sort of lay the groundwork here. Postgres itself, you can download the source code from postgresql.org, compile it, install it on two machines, do some configuration settings. Postgres gives you a pretty solid capabilities around replication. It will replicate data from the first server to the second server. But Postgres, what it won't do, it'll give you kind of APIs that could convert the replica into a primary, but it won't do cluster management, right? It won't automate failovers or automate adding new clusters and new configurations. So if we want to run Postgres on Kubernetes, and if we want things like self-healing or automated failover, then one way or another, we're going to have to provide these capabilities. It's not in core Postgres, right? And the second really important point to lay the groundwork for our talk today is to understand that Postgres's replication capabilities are incredibly versatile. Postgres it can be configured in a lot of different ways. And this is kind of classic Postgres in a way. There's a lot of configuration settings that are exposed. There's a lot of flexibility in there. And it's important to understand that the cloud native PG operator provides an unusually high level of access to that configuration and to that versatility. Cloud native PG will let you configure Postgres replication in a lot of different ways. Okay. Now, why would you want that? Why is that interesting? The reason is because that allows us to fine tune a lot of the trade offs that are involved in replication. Three of the areas that are talked about the most often would be the three that I've circled here on this screen, which are durability and availability and performance. But before I can talk about these trade-offs and how you might tune them, first I need to just give you a very quick introduction to replication with Postgres and Cloud Native PG in the first place. So I'm just going to real quickly run over how do you even configure this to get started. Basically, there's four things that you need to know if you want to configure replication with Cloud Native Postgres. Let's run through these. And then there's a couple more on this slide that you can look up later on your own, but let's run through the four main things. First, and by far most important, is this concept of synchronous replication. Now, what is synchronous replication? Synchronous replication is related to really one of the core properties of any relational database, and that is transactions. Okay. And this is really fundamentally, it's about a promise that we make to our developers and to users of our platforms, which is the reason, one of the big reasons that people find relational databases so valuable to use. So, this idea of a transaction, what's the promise that we make? The promise is, well, you could insert and update and delete as many records as you want. You can make all these changes. You can call procedures and functions, run calculations. But the magical moment is when you execute this magic keyword, the keyword commit. And every programming language has this. I have some examples here on the screen. When you say commit, that is the key moment when all of your transaction, everything that you did in that transaction, it becomes visible to other connections on the system. And importantly, that's also the point. That's the moment where we promise to you, the developer, that the effect that that transaction won't be lost. It's durable, it's persistent. And even if there are failures in the system, they don't need to try to design their whole application around maybe failures that could happen underneath. Like as a database system, we'll handle failure scenarios and we won't lose your data. Okay, so this is a promise that we're making. Now, synchronous replication has to do with, well, first of all, replication is a key part of how we keep that promise and how we make that promise, right? Because if there are failures in the system, the data needs to be replicated. Synchronous, I'm a little bit opinionated about synchronous replication. It's not something that's enabled by default with Postgres for good reason. You don't necessarily need it everywhere. My personal opinion is if you're running Postgres on Kubernetes, then I do think everybody should use synchronous replication. And what it basically means is when that commit statement is acknowledged to the client, when you tell the client the commit was successful, we're also telling you that the transaction has been replicated. That's the key thing with synchronous replication. And in fact, the way the Postgres source code implements synchronous replication is even that a huge chunk of that logic is right inside the processing for the commit statement itself. So what synchronous replication means, actually, let's take a quick deep dive into synchronous replication very briefly. I grabbed the commit message this is from actually almost 10 years ago. It's crazy how long this has been here. And I've circled on the right-hand side the single all-important parameter that you need to know about, which is called synchronous standby names. This is the one parameter. This is the most important parameter when it comes to synchronous replication in Postgres, and it has three components. If you look at the bottom part that I circled here, or the bottom circle, it's in the middle of the screen, there are three components. There's a method, there's a number, and there's a target set. Easy to remember. Method, number, target set, right? The method tells you, and a lot of people don't even realize this, that Postgres has two different methods of doing synchronous replication. Priority has been around forever, but even quorum-based replication has already been around for almost 10 years. The method tells you which of those two. The number is how many destinations am I promising that the data is replicated to, and the target set is the complete set of destinations that we are replicating to. So I might have 3 target replicas, and I promise that every transaction is replicated to at least 2 of the 3 before the commit is acknowledged to the client. So that's your crash course on synchronous replication. What is the second thing you need to know? The second thing is this is specific to cloud native Postgres, and it's the concept of data durability. Why do we have this? Well, Postgres itself is very literal. Okay. If I tell Postgres, I want you to replicate the data to one destination, well, Postgres was going to make sure that that transaction has been replicated to one destination. But what if my one replica is having what if I'm patching? It's offline for maintenance. There's some sort of momentary issue where it's unhealthy. Well, Postgres is going to keep its promise, which means no transactions are going to commit at all, right? Until that replica is healthy again. Now, this might be the trade-off that you want if you absolutely want to guarantee the data durability, but it might not be. Maybe what you want is if a node is offline for patching or maintenance, then temporarily we let the transactions flow until it's back, and then we keep our promise that everything is durable. The terminology for that in cloud native Postgres is called preferred data durability. By default, the durability is what's called required, but you have the option to set it to preferred. And this is what cloud native Postgres will do is CloudNativePG Operator itself understands the health of the replicas. And if a replica is unhealthy, it can on the fly reconfigure Postgres to lower the replication configuration and then raise it back up once the replica is available again. The third thing that you need to know is that I talked earlier about in the all important parameter, the method, the number, and the target list. We've talked about the method and the number. This is how you control the target list. There are 3 settings in Cloud Native PG that give you control over that target list. I'm not going to go super in depth on this right now, but know that these are there. And the fourth thing is a separate Postgres parameter called synchronous commit. And this parameter is the one that lets you fine tune what exactly do we mean when we say replicated. Does it just mean that the transaction has been received by a replica? Does it mean it's written to the log file on the replica? or and durable on the log file, or does it mean it's fully applied to all of the tables and that connections, read-only connections on that replica can actually see the data? So this lets you fine-tune that behavior. Now, once we have these 4 tools in our tool belt and we understand these 4 fundamental concepts, now we can talk about all those trade-offs that I mentioned earlier. And what I'm actually going to do here, I'm actually going to take some terminology from Oracle because I think that this terminology is really great terminology. Oracle came up with this ages, like a long time ago, Oracle Data Guard. They talk about maximizing performance, maximizing availability, or maximizing protection. And what I've done in this table here on the screen is I've shown you for each of those trade-off sort of decisions, how you would do that with Cloud Native PG, right? So using the 4 tools that we just talked about in the right-hand column, you can see the Cloud Native PG configuration to maximize any of those properties. But this is just the beginning because we can do even more. I'm showing you here like a high availability setup within a single Kubernetes cluster, right? Where you have a primary and 2 replicas, but we can also do multiple Kubernetes clusters. So here's an example. You might think traditionally like a DR setup where maybe you have a second data center with a separate Kubernetes cluster in it. And here, Cloud Native PG has HA in the primary cluster, and it also has HA in the secondary cluster, and it's replicating between them. And we can make all of the same trade-off decisions between multiple data centers or multiple Kubernetes clusters. So here's an example of maximizing performance, and I'm showing you in the box on the left side what the Kubernetes spec looks like, and on the bottom of the screen, it shows you the Postgres configuration. Here's an example of maximizing availability, slightly different configuration and different trade-offs, but the same setup. And here's an example of maximizing protection, but we can still go even further, believe it or not. This maximum protection configuration guarantees that it's replicated, which means if the remote data center, if you have a network issue, if the remote data center has problems, your primary data center stops accepting writes. That might not be the trade-off that you want. Well, you can even do multiple Kubernetes clusters, and Cloud Native PG will allow this configuration. So this way, you're guaranteeing that every transaction goes to at least one of the remote clusters, but there are 2 of them there, right? Now, this incredible flexibility leads us to a gigantic problem, and this is the reason that we're having the talk today. The problem is, if we're going to let you have all of this flexibility and let you configure all of these different ways, how in the world are we going to keep track of all of our source code? And how are we going to make sure that all of our failover logic is correct, that we don't make any mistakes? And like, what if that you have that topology with multiple data centers and multiple clusters and you have failover logic that has to do failovers correctly and keep our promise that we made to the developers that we won't lose any transactions. This is actually a really hard problem. It's a really tricky problem to solve. Um, so this is something that we've been thinking about over the past couple of years. And as we were thinking about it, the realization kind of dawned on us that there was a very elegant and simple solution to this, an approach that we could take that would solve literally every possible configuration that you could come up with for Postgres and on Kubernetes with clustering, do it correctly, provably guarantee the correctness, um, and handle it pretty simply. And basically, all we had to do was take a concept that has been around for decades, but it's not a concept that people normally think about in sort of the Postgres space, and we applied it to Postgres. And that concept is sort of now I'm getting in the design, and I have actually a picture which is basically from Leo's whiteboard back when we were throwing ideas back and forth, and he took a picture of it with his phone and dropped it on Slack because we're all over the world trying to collaborate. And what we did is we took this basic concept of like readers and writers being greater than the node count, the replication factor, and we applied it to Postgres. Now, you might be familiar with this if you've read some of the DynamoDB papers or if you've configured Cassandra, but it's not something traditionally applied to Postgres. Now, what we've done with this is we've mapped over the concepts to Postgres on Kubernetes. And very specifically, what we're doing with this is we're sort of treating it like a gating function. So it only really applies when we're doing a cluster reconfiguration. So something like a failover, a promotion, adding nodes, removing nodes, just reconfiguring the topology of the cluster. And what we've done is the n value here is basically, it all goes back to that all important Postgres parameter I talked about earlier, synchronous standby names. Okay. The n value is the target set. The w value is the number. And the r value, we only need to evaluate if we're trying to make a decision about reconfiguring the cluster. It is the intersection of the set of promotable replicas with the set of targets. Okay. The best way to describe this is just to work through a couple of examples. So let's just take really quickly and look at this one. This is the maximum availability configuration with a replica cluster. And I'm going to suggest to start by looking at the bottom of this slide. We have the setting, the left side is what you configured. The bottom is what is how CNPG set Postgres up, synchronous standby names. That's that all important parameter. So look at that setting and let's work through what our formula values are. First of all, the n value is the target set. The target set has three members, Angus, ACDC2, and ACDC3, so the n value is 3. The w value is just a number, you pull it straight up from the bottom. And now let's suppose that we have a failure. The primary instance fails, and now we need to ask the question, is it safe to do a failover or to promote one of those replicas, okay? So now we have to figure out what is our set of promotable replicas because we lost the writer. The promotable replicas are just the two local instances because that's the operator works within a single Kubernetes cluster, okay? So our R value is 2. 2 plus 2 is 4. 4 is greater than 3. The check passes. We can continue. So now what CNPG can safely do is just look at those two promotable replicas. Whichever one has the most advanced LSN, it will select that one. It will do a promotion. And we're able to guarantee that there's no way that we lose any transactions when this happens. You can run exactly the same exercise with a couple other configurations like maximum protection. I'm not going to walk through these in depth, but here's an example where the intersection only includes one of the two promotable replicas. You'll see that the formula still works and it lets it continue. You can even do this with multiple Kubernetes clusters targets. Here's the n value is 4, the w value is 3. This is showing two replica clusters, and this is showing how the formula still passes. We can also look at a situation where we lose one of the replicas at the same time as the primary, and this gives you a good example of a case where the the algorithm correctly puts us in, tells us like this is a situation where we can't guarantee that you won't lose a transaction if you do the promotion. So the best decision here is to put the cluster into a state that requires manual intervention. You want to get a human in the loop to make a decision about what we should do. And that is the correct outcome. That's the outcome that we got here. And last but not least, you can run scenarios, and this is one of the most interesting things, is to run scenarios that involve network partitions. Now, if you're going to look at network partitions, you do need to start thinking about the placement of the operator, not just the nodes that are available, because you need to think about which side of the partition is the operator on. Here's an example with the primary instance being partitioned off. Here's an example showing one of the replicas being partitioned off. And one of the most interesting scenarios you can look at is a scenario where the operator ends up on one side of the partition with a replica, and the primary ends up on the other side of the partition with another replica. And again, this is one of the places where the algorithm really shines. Because in this situation, the primary and the replica in the second partition will continue to accept writes at least for a couple of seconds, even with something like failsafe in place that eventually detects, right? And so if you allow the operator to make any kind of an automated promotion decision at all, there's always the risk that a couple of transactions can get lost. And this algorithm enables us to correctly handle this situation to guarantee no transactions will ever be lost, even in a split brain or a network partition scenario like this. So that's a high-level overview of the algorithm. Now I'm going to hand it off to Leo to go a little bit deeper on how things work.
Thank you, Jeremy. So, how is this working on CNPG? So, first of all, you can see we added a new configuration panel. It's called failoverquorum, and you can find it in the Synchronous replication configuration. This actually is totally linked with what Jeremy was saying before, and starting from version 1.28. Okay, it's good. But when this parameter is enabled, what will happen? So this is twofold. First of all, the operator will start working and create a new custom resource. And the instance manager will keep it updated. So let's see an example in the next slide. And that's it. This is the custom resource we created just for that. So you can see it brings the same name as your cluster. And in the status, you will find the exact same information that you can find in the Synchronous standby names configuration parameter. So look, method any, and on the right, any, standby number one, and the list of standby names, most popularly targets. But who is the real source of truth for this information? It's just Postgres itself. Most appropriately, it is the Postgres running on the primary instance. So the instance manager, which is our PID one that has the postmaster as a child process, will keep it updated. We can see it in the next slide. Then we have this important question. Let's suppose we change something, we reconfigure something in the cluster. What's going to happen? How can we be sure that actually Postgres loaded the most recent configuration? This process is asynchronous. So the only way we could do it is to just start from the beginning, from the custom resource to the end, to the Postgres configuration. That's something that makes this, let's say, easier for us. And it is that when you configure Postgres using CloudNativePG, you are forced to use the cluster custom resource. You cannot just connect to the Postgres pod and change the configuration itself unless you force the system. So in the next slide, we can see what happens when we change a Postgres configuration. So we regenerate a new configuration file. We will see it is called custom.conf, and we include it from the main Postgres config. We update it, and then we reset the failoverquorum custom resource. So basically, we take out all the status. And from now on, automatic failover is disabled because 0 plus 0 is not greater than 0. Then we sig up the postmaster. And Unix signals are asynchronous, so we need to wait until Postgres received it. And when we are sure that Postgres received it, then we can update the failoverquorum custom resource again using the actual Postgres config. From now on, if the conditions are met, automatic failover is possible. But the main question is, how can we wait until the postmaster receives the new configuration? So we answer the question and we bring another one. And that's it. That's what we do in our custom.conf. So, as you can see, we have a few custom parameters. The first one is called CNPG.synchronous standby names metadata. It's just a JSON string, and you can find there all the information that you can see in the status section on the failoverquorum custom resource. It's nothing too fancy. And when we created the custom conf contents, we also compute a hash over that, and we store the hash too. And having done that, we can see in the next slide that we can now wait after we sig up the postmaster. We can now wait until Postgres gives us the same hash that we put inside the configuration file. The postmaster will eventually catch up our sig up and reload the configuration. So when we got back the hash we know, we are sure that the configuration was loaded. And after that, what's going to happen? So in the next slide, we can see that we can read back our JSON string. And this is exactly what we need to update the failoverquorum object. So from this walkthrough, the really important thing is that Postgres is the source of authority here. It's not us, it's not the CRD, it's not the Kubernetes controllers. And so from now on, if the conditions are met, the operator will be allowed to trigger an automatic failover using the information it has. So in the next slide, we have back this magic formula. And we have all the information inside failoverquorum, and we have all the latest information from the real cluster observed status. And now we can decide, do we really want a failover or not? If we don't want a failover, then it's fine. We can just wait until the situation change or until someone actually promoted a replica. If we want it, then we proceed, because now it is safe. So let's have a look at this example. It is just an exercise, but it's a situation that is commonly deployed. So this is just a 3 instances cluster with synchronous replication, because I totally agree with Jeremy, synchronous replication is absolutely important. We choose to have with number 1 just asynchronous replica, just one, and we activated failoverquorum. And what happens now if the primary goes down? So we are sure that one of example 2 and example 3, they received all the transactions. So we meet the action one. It's safe to failover to the most advanced replica. Even if we don't know which one, we don't know if it was example 2 or example 3, but it's safe to failover to the most advanced one. This is the important point. You can see on the right, there is a log message. You will find it to your operator log, and it tells, is strongly consistent, true. Yes, that's the most important point. Okay, so in the next slide, oh, this is bad. So what's happening now? We lost the primary and we lost the replica too. It is exactly the same scenario as before, but now, since we don't know whether it was example 2 or example 3, having all the transactions, it's not safe for us to failover. And you will see in the operator that message, strong consistency check failed, because now that magic formula is not correct, because 1 + 1 is not greater than 2. And if you happen to be in this situation, you need or to wait until your situation change, or you promote manually a replica after you are sure that everything is good. But then you are on your own, but you are safe. So yes, that's it, just in a few words. And so that's it. As Jeremy was saying, it's really a nice time to be in this community. And if you like to chat with us, to contribute back, we really hope you enjoy CloudNativePG as we do. This is our link to GitHub and also our Twitter, X account this time. Okay. Thank you so much.
Thank you.